of a pump or a fan. Okay, so this is the graphics screen an operator would typically see. He has direct control over manually slowing down or speeding up this VFD. So Jay, go ahead and speed it up for us.
You guys can also see it turn here.
Should be turning there, hopefully. Speed it up one more time. All right, well, now we're just going to show that this exploit works. Paul, can you slow it down for us? And speed it up one more time for us. Now this is pretty dangerous. I mean, when you get direct control over a component as powerful as a VFD, you're directly controlling how much material is forwarded to some other area of the process, whether it be steam or coal or slurry or whatever. So both upstream and downstream components can be affected by this. This is a very dangerous situation. The second system we're going to simulate today is Annunciators. Jay's going to get that set up for a second.
It might not work. I'm going to have to disconnect first.
All right. Yep. Good. Okay. Annunciators tell the plant operators of problems. They're kind of like alarms. Plants usually have a few alarms flashing all the time just due to maintenance activities or faulty equipment. They know about these. They know which ones are false, which ones are real. Physical annunciators usually accompany the software annunciators you see up here today. We're not going to simulate those because we don't have the hardware. But anyway.
We have to dump the program in and restart the application every time we do this, so that's why it's taking a little longer.
Yeah.
But we're almost there.
Variable frequency drive. What it does is it varies the frequency that's sent to a three-phase motor. It also varies the phase, which changes the direction. You vary the frequency to change the speed.
You gotta reconnect.
They're very common in the power industry. They're very powerful, very useful stuff. They can be. The model we have here does have a network connection. We're not using it today, though. Okay, so this is what you typically see on an operator screen. You see a few alarms flashing due to maintenance activities or whatnot. No big problems. And now we're going to show Paul has full control over the annunciator screens. All right, so Paul just said hi to the operators. Now you could do this. You could say hi or FU or whatever you want to the operators, but ultimately if this was a real attack, that wouldn't be the goal. The real goal would be to suppress the alarm so the operator can't see what you're doing in some other area of the system. This would cause more damage with your attack.
So just having control of the annunciator has control of the output, not the actual alarms going off? He's not causing the problem? He's just
No. He's just suppressing the operator from knowing about the problem. Yeah. It can, because sometimes these annunciators are controlled, the annunciators that are on the walls, they're controlled by lights in the back. They're often controlled by a PLC just like we have here today. So if you get control of one, you get control of another.
Are the controls that difficult to read on a real screen, or is it just the projector?
It's probably just the projector, I'm sure.
They have to see the controls, otherwise they have trouble.
If I took and I started that cause on this system over here, that's going to redirect body, not suppress it, maybe do that.
Well, if you get
your attention to fixing what the hell is going on, right?
If they see something like that, they may just shut down, they may trip the whole plant. They may just stop the plant from operating because they have no idea what's going on. They no longer have control over the plant.
that would freak out an operator right there if we did that.
Yeah, but I mean, I've got attention focus there, just like Gallagher.
Sure. Okay, so the third system we're going to simulate real quickly is the bottom ash system. So what happens is you have a boiler, a burner, FD and ID fans, which are forced draft, which blow air into the furnace and induce draft, which kind of suck out the smoke and the ash. You also have water tubes running down the side of the boiler and tubes hanging inside the boiler that all feed steam to the turbines. There's two types of ash. There's fly ash and bottom ash. We'll exploit the bottom ash system today. So I'll just give you a quick overview of how the system's supposed to work. The hopper's filling right now. That's what the green means. The fill valve up top is open. Now the drain valve opens, the hopper fill valve closes, the crushers crush the slag that's melting down the sides of the walls. Now the spray valve opens and sprays the little bit of extra stuff that's stuck to the walls, and the process starts over. It fills again, etc. Okay, so now you're going to see Paul exploit this system and cause a real mess.
Hold on a second.
Just a moment.
To get to zero. Go ahead.
Okay, so now Paul is setting the state back to 1. The fill valve is open, the drain valve is closed. You saw what's supposed to happen. The drain valve opened for a second and closed again. The fill valve open, and you're just filling that hopper all the way up. Eventually what's going to happen is water is going to get inside the boiler. You could put out the flame, possibly cause a boiler explosion, at least hypothetically. If you also have control over the annunciators, the operator might not know about this. If you have control over other systems, this might go completely undetected for, many, many minutes. And you could have a real mess that could take weeks or months to clean up, possibly fatalities.
You say a real mess takes weeks or months to clean up. What's the effect of that to the power grid?
It depends on the facility. It really does. If it's a 2 gigawatt plant, it could affect the grid as a whole. That's specifically what NERC compliance is focusing on, is protecting the grid as a whole. So if you generate, 2 gigawatts or more, you got to be concerned about that. It also depends on how quickly it happens. If it happens real quickly and you lose units completely and people are unaware of it for a little while, it could take out a lot of area.
If the plant is unique, each plant's designed on its own, you've got to do some serious discovery to understand what the PLC is doing.
Yes.
Absolutely.
Yes.
You're going to have to do some insider discovery to find out.
Right.
What this
A lot of this information is publicly available. A lot can be obtained via social engineering. You do need to know a little bit about the process. I mean, this is one thing we're trying to get across to you all today. It's kind of a new concept called malicious process design. Process design is something we do all the time, but designing it to be a dangerous process, sometimes it happens inadvertently. We're kind of afraid that it might happen intentionally in the future.
The other problem with that, to address your point, is if you were at the talk earlier, he talked a little bit about that, how you have to know both sides, not just how to get into the system, but what to do once you're in there. The problem is that, first of all, if you're already on the network, a lot of this stuff you can probably find on there, and there's all kinds of vulnerabilities. There was one released recently about Siemens, about how you could get access to essentially the process map. So in addition to that, it could be there have been instances where ex-employees, I think there was one in Australia in a waste management plant, who already knew the entire system. It was a contractor who knew the system. It's not impossible to know the process, or if you don't know it, to get that information.
Right.
Yeah, way back there. Yeah, you.
Yeah, can each of those dangerous operations be triggered with like a single click or a single keystroke?
Unlikely, but possible. Different systems are designed differently. You have to understand there's like 5,000 power plants in the United States built between 1940 and a year ago. Whatever you do, it's going to have to be plant specific. It will always be plant specific. They're all just designed completely differently.
Quality assurance and independent verification and validation is done by who?
There are quality assurance engineers that do that. Nuclear is much better than fossil right now, but it's starting to get better. Sorry, I didn't hear you.
Typically, in an organization, those are independent, so that the box isn't watching the shipment.
Yes, that is true.
You didn't notice that in your organizational structure.
That's true. We should have put a QA in there. I guess in my experience, QA isn't always required for things like CT sites, combustion turbine, combined cycles, or even fossil plants. Yeah, we're trying to. Well, typically designers are separate. We design them, or we lay out the basics. They draw up the drawings. What's supposed to happen is supposed to go to a QA, but in a lot of organizations, QA is just like a mechanical engineer who's reviewing control system drawings, electrical drawings, civil drawings, etc. So, I mean, nuclear is much better at this than everybody else. You ready? I think at least one or two of them are already known about, and their response was to, make sure it's running on a secure network, to unload it on the client. Yes, sir.
What about vendor-required backdoors? Specifically, certain turbine vendors require a connection into the turbine at all times to constantly tweak and keep the turbine at maximum efficiency.
I've heard of connections similar to that. I haven't heard of that one specifically.
That's completely true. I mean, a lot of times they require that you have that connection there for to maintain your warranty, so that they can monitor the operation of the turbine and make sure you're not doing something that's going to void the warranty. And that's definitely a vulnerability that could potentially be exploited. It's something that a lot of times doesn't even go through a DMZ. It's just a connection straight to a vendor.
Correct.
Mm-hmm.
Yes, sir.
At the NSA, you can't use a coffee maker, a blender, even a cat box unless it has common criteria testing. Basically, everything has to be validated to be used in any kind of a secure environment.
Right.
Would it make sense to have something in basically the same type of common criteria for any system that's going to support any part of the grid?
Agreed. Nuclear already does that. They're really strict about this stuff.
With fossil, all of that stuff is privately owned, so to be able to get agreement on that kind of stuff is it's an undertaking.
That's what these standards are trying to do. The problem is there's so many different standards spread out, different organizations. Sometimes they overlap, and you don't know which one you have to comply with the most. It's a real mess right now in terms of the standards that people are trying to comply with, and also there's a lot of resistance. People don't want to change. It's also very tough for a plant that was built 50 years ago that was modified slowly, decade after decade.
I mean, there is a lot of healthcare systems, information systems they have. I'm not sure what they come under, but they go through pretty rigorous testing. It seems like a lot of this has already been done, trailblazed before, and whether it takes regulation or something like that, it shouldn't be that hard to bring it to the non-nuclear side.
I agree. The problem is one of the points Paul made is it's bad design. I mean, these PLCs just simply were not designed with security in mind. They were designed to get out quickly as possible, to make the most profit, and to give functionality, good functionality. And they do that well. But in terms of security, there is none.
I understand it's a complicated system and there's a full need for a local area network, but I'm really not sure why there needs to be a connection out to off-site. Basically, you have a self-contained plant, does everything it needs to do, and you do have less need for that individual password. It seems like you shoot yourself in the foot if you don't have an air gap.
Well, there is somewhat a need. You've got so many power plants generating so much electricity, each with a different amount. Then you've got renewable sources coming in now. And when you look at the graph of how much energy we consume in a day, it's like this. It's up and down. So that all needs to be coordinated. How many megawatts is each plant generating? Which units go up? Which ones get priority? I agree. If there's a way we can do it without having a connection to the outside world, we should. I don't think we've determined how to do that effectively yet. I mean, even in the olden days, I think they used telephones or something, But, yes, sir.
I was in a SCADA class with someone that worked at a
power grid. And what they said is that between their SCADA networks and their business